How's everyone?
Just had a pizza.
Pizza, excellent. I'm gonna make a pizza
I got
after
a
class.
Calexico for mod pizza.
Oh, nice. Best thing about mod pizza is the desserts, in my opinion,
Yeah,
because they have like those homemade ring dings.
I really like the Calexico because it's got gorgonzola on it and buffalo sauce.
Oh, yum. That sounds amazing. All right. Well, any questions? We're kind of done with set theory for now. We'll be using set theory for, a lot of other parts of the course, but we're kind of done talking about it as a main topic.
Can we talk about number 8 on the homework, the one about the university set? And then, I figured it out logically, I think, just doing the math, but, as far as set theory is concerned, how do you write all that out when you have numbers and, sets?
So we're actually going to come back to that. That uses something called the principle of inclusion exclusion, and it actually belongs in a different topic when we talk about counting, basically, which will be in a few weeks. So putting that problem in this set is exactly what you did. Exactly what I was hoping people would do, which is think about it logically and sort of figure out, what the answers might be. And like I warned you, I'm not going to grade that one for credit. Um, but I just wanted people to sort of have seen that problem and thought about it, and then we're going to come back to that later on and see a very precise way to do that by counting the number of things in sets and taking care of where there is overlap.
I wound
Cool,
up
thank you.
Yeah.
misreading the homework problems at first, and I did number 8 on 1.3 and thought that was the one you wanted us to try.
Oh, okay.
I still did the 1.2 one because I figured out I misread, but I thought it was like, so you're trying to get me to count all of these coins that this person's pulling out of their pocket and how many sets they can pull out.
Ah, okay.
I was like, this isn't too bad.
All right, let's see. Kind of a weird question. So yeah, there will be homework every week, and homework 2 was posted this morning. And there's going to be 2 programming assignments, and that's it for work in the class, other than the midterm and the final exam. Um, and I'm assigning particular problems from the homework that I think will help with the concepts and so on. But you're absolutely welcome and encouraged to do more problems. I believe the odd numbered problems have solutions in the back of the text. And so, if you want to self-assess or you want to get more practice, you can work on the odd numbered problems, and then look in the book and see if you're getting the right answer and so on and so forth.
When are we going to do some programming assignments for this class?
I think they're going to start like week 7, maybe. They're going to come out pretty late, and we're not going to really teach programming in this course, but we're going to use it as a tool to go back and address some of the topics that we're talking about from a different perspective. So sometimes I'll give an assignment where people will write a program to do basic set manipulation. Let people type in, the elements of sets and then calculate the union and the intersection and so on and so forth. So things like that. So they'll be coming down the road, but there's a lot of material in this course. We really cover several different topics. We'll do proofs and propositional logic right now, and then we'll go on to some number theory, and then we'll come back and we'll talk about another aspect of proofs and logic called mathematical induction. And then we'll do a unit where we talk about counting and learn some rules related to that. And we'll do some graph theory. We might talk about trees. We might talk about Boolean algebra. We'll talk about formal languages and state machines. And there's just a lot of stuff that we do do in here. So definitely, you know, work on other problems if you want to get some additional work, but I don't want to dog you with you know, homework sets every day or something like that. All right, so hopefully everybody turned in homework 1, and I will try to get that graded before Friday, and I'll post grades and some feedback, and then Friday we'll talk about homework 1 in class, and I'll sort of, you know, share general reflections and so on, specific issues and such. I've posted homework 2. You can take a look at that assignment, but that's going to, it works a little bit with some more stuff on sets, but mostly it's going to deal with chapter 3, which is on logic and proofs and propositions, which is what we're starting right now. So I'll go through the assignment write up for homework 2 on Friday also, and if you have questions about what is this question asking for and so on, you can bring them up then. So let's move on to our next topic. So topic 2, propositional logic. And this is basically like proofs. Okay, so proofs are about, you know, being able to formally show that something is true. And so, you know, A union B equals B union A. Well, if you think about it, what's the union? It's all the stuff that's in A, all the stuff that's in B put together. Well, what is B union A? It's the stuff that's in B and the stuff that's in A put together. Yeah, logically, they should be exactly the same thing, right? So how do we prove that? Well, we can do demonstrations. So in one question, you were asked to demonstrate certain rules. So you could say, you know, here's set A. It's got 2 pens, and here's set B, which has a mouse, and the union is these 3 things. And if I start with a mouse and 2 pens and I take the union, I get the same set of 3 things. And we can draw Venn diagrams and shake our head and say, yeah, this looks right, but how would we actually prove it? So we could do something like, you know, use a membership table, our set theory version of truth tables. And we saw we could use that to actually show that in all cases, A union B will be the same as B union A. But there's some things that we're going to want to prove that we can't just write, you know, an example that shows this is feasible, or draw a Venn diagram or something like that. And this will have to do with formalizing how we can state what it is we want to prove, and then defining the steps that we go through to actually do that proof. Can you do A minus B not equal to B minus A, just to make sure I have the right concept? So is this a homework question you're asking about, where you were asked to demonstrate that?
Yeah, it was on homework 1. I just want to make sure that I got the right understanding.
So if I remember this correctly, the universe was the set of numbers up to 10. And it said, you know, demonstrate an example where A minus... up to 9. Demonstrate an example where A minus B is not equal to B minus A. So I could say something like, you know, let A be the set containing 1, 2, 3, 4. Let B be the set containing 3, 4, 5. So now I would say A minus B equals, and I would do that calculation. So A minus B says start with A and toss out anything that you find in B. So I'm going to toss out the 3. I'm going to toss out the 4. There's no 5 in A, but that's okay, right? I'm starting with A and I'm tossing out the 3 and 4, so this is going to be 1, 2. And then B minus A, I'm going to start with B and toss out anything I find in A. So the 3's got to go. The 4 has got to go, but the 5 can stay. So B minus A is just 5. And, you could be done there, but I would just kind of drive the point home. This is not equal to that. And
Okay.
so that's an example where A minus B is not the same as B minus A.
Okay, great, thank you.
Mm-hmm. So the first homework in this course, right, gets graded more gently than the ninth homework in this course, right? So if you're concerned you didn't use the correct notation or terminology or something like that, right? I'm not going to, jump up and down and say you used a parentheses instead of a curly bracket, right? So I'll give you a lot of feedback on the assignment, but I'll also cut you a lot of slack, right? And as we move forward, right, the constraints will get a little tighter probably, in the expectations. But we're here to learn, right? And I don't think homework should be just something like good or bad, right? That's not the point. I mean, you need a grade for the course because we're required to give grades. But the real point of the homework is to further learn and understand the concepts. And so I like the homework to be a learning experience, and I'll try to give you feedback on it. And I encourage people, even if so typically I grade one problem, even if you got 100% because that problem was correct. If you're unsure what the other problems, if they were right or not, let's talk about it, right? So you got to do the homework, and it does, become a part of your grade, but don't get too worked up over it in the sense of don't think of it as just something that you have to deal with. And I don't want the grading to take away from the learning, basically. All right, and if you did not turn the homework in late and you want to use a slip day, send me an email. Remember, nmacias@clark.edu. Don't use Canvas email. Send me an email and just say, hey, I want to use one slip day for homework 1. And I'll make a note of that, and then you can turn it in by 8 o'clock tomorrow morning and have it graded for full credit. All right, so propositions. So mostly what we're going to be proving are these things called propositions. So what is a proposition? So a proposition is a declarative statement that is either true or false. It's a really simple definition, but it's really important, and it's very easy to forget this definition. So a declarative statement that is true or false. Today is Wednesday. That's a proposition. Today is not Wednesday. That's also a proposition. Wednesday is not a real day. That's a proposition. I'm just making up stuff. That's a proposition. So it's a declarative statement that is true or false. So what time is it? That's not a proposition. That is not declaring something, and there is no truth value to the statement, what time is it? There's no truth value to the statement, hello. Have a nice day. Right? Those are not declarations. But this is fun. That's a declaration. And it has a true value, or that's either, true or false.
How about hello, you look great today?
Yeah, I would say that's probably a proposition. The hello part in the beginning is a little weird, but this is one of the things about this subject is, we usually interface through spoken or written language, and English in particular is very imprecise a lot of times. In addition to being one of the harder languages to learn, it's one of the more ambiguous at times. So for example, you're at a restaurant and the wait person comes over and says super salad, right? And what they're really saying is, would you like to have the soup or would you like to have the salad? You can pick one, but you can't pick both. But, it just says super salad. And from a propositional logic perspective, the correct answer would be true or false, yes or no. Right? So as we talk about propositions and propositional logic and proofs, we're going to be talking about it in English, and we're going to be trying to describe things that have very, very precise meanings. And sometimes those will bump up against each other. And so we'll talk about that when that happens. Super, that must be a great salad. Excellent. All right. So this is the main thing we're studying, are propositions. And the reason I'm spending a few minutes talking about this is, here's an example of a proposition. X equals 5. Here's another proposition. X minus 5 equals 0. And if this proposition happens to be true, I know that this is also true. And if this is false, I know that this is false. So from one proposition, sometimes we can write other propositions. And this is what our proof is going to be. When we try to prove something, we're going to write a series of propositions, and each of these propositions is going to be true, and hopefully at some point we'll write a proposition, which is the thing we're asked to show. So someone says, prove to me that the moon is made of green cheese. And so we'll start off, okay, well, 1 plus 1 equals 2. And 2 is an integer. And we'll argue a series of logical statements. And if we can eventually get to the point where we can show the moon is made of green cheese, we're done. We've proven that. All right? All right, so here's something. So these are propositions. Here's something that's not a proposition. X plus 1. Right? This is an arithmetic operation or an algebraic expression. It's not a statement that we can say this is true or false. Someone comes up to you and says, X plus 1? What are you going to say? Right? But if someone comes up to you and says, is X equal to 5? Well, assuming you know what X is and you know what 5 is, you can say yes or no. Did people really believe the moon was made of cheese?
So I have heard, and that was like one of the silly things about the 100-year-old movie, A Trip to the Moon.
Oh, really?
Yeah.
I'll have to watch that again. I know Wallace and Gromit did that, but...
Yeah, there's like a super, super old, like 115-year-old French movie called Trip to the Moon, where they get into like a bullet and fire a cannon to the moon.
Cool. I'll have to check that out. All right, so propositions. All right, so a lot of times when I'm grading people's proofs, I will see things like this. And if I do, I'll write, well, I won't be writing on it because we're still remote, but I would write something like not a proposition. And that means come back to day 1 on this unit. And what is a proposition? It's a declarative statement that's true or false. So yeah, that's not a declaration. That doesn't have a truth value. All right, so we'll bump into that a bunch. All right, so that's...
To have an equal symbol somewhere to be a preposition, right?
If we're writing an arithmetic expression that's going to be a proposition, we would want to compare, right? We could say, for example, x is bigger than 5. That's a proposition. We could say x is not equal to y. That's a proposition. But if we just, write x squared, that's not a proposition. And that's mostly where this confusion comes up, is when we start doing arithmetic, because we're so used to writing things like this. But even though we're writing, things that look like mathematics, we got to remember we're trying to write propositions. So they have to be things with truth values. All right, so we're going to talk about propositional variables. And it's just like a variable in a programming language, or in algebra for that matter. So this is usually a single letter that represents a proposition. All right. Suppose we have the proposition that today is Wednesday, and I want to use a propositional variable for that as part of a proof. Okay, here's a correct way to write that will get you full credit for this part of your proof. So let P be the proposition. Quote, today is Wednesday. Okay, if I see something like this in the beginning of your proof, I get a smile on my face. I'm like, oh, this is going to be a good proof to read, right? So this is good. You are stating in, plain words, P is a proposition. It's the proposition today is Wednesday. All right. If you're rushing to finish your homework because it's, 7:45 in the morning and it's due in 15 minutes, you may do something like this. P colon, today is Wednesday. If I see that in the beginning of your proof, that's what we're doing, right? So I understand what you're trying to do. You're trying to say P is a proposition which stands for the statement today is Wednesday. But it's not quite as formal. And if you really want to bum me out, P equals today is Wednesday, right? And that's like a really, really quick path to a lot of troubles in a proof. Because this is an arithmetic assignment statement. This is a propositional variable. This is a sentence, right? And this will almost always get you into trouble in a proof, right? So don't do this. Don't do this. Do this. And it may seem like just a matter of notation right now, but guaranteed, once we start doing proofs involving arithmetic expressions and algebraic equations, doing this will trip you up. And doing this, your colon will start to look like an equal sign as you work through your proof, and you're going to end up doing the same things you do here, right? So spell it out. Let P be the proposition, boom. And that's always the beginning of our propositional proofs, is stating a proposition, right? So I might follow this with, prove P, or prove not P, or something like that. Oh, that's cool. So someone had a bio class, and the teacher said if you could deliberately get a 0% on the multiple choice, you'd get 150%. That's a good challenge, and definitely a big gamble, because if you mess up just once, you might get like a 4 or something. Hey, I kind of like that, though. Like if you could write a program and no line of the program would compile. Something like that. All right, so this is sometimes called propositional calculus, if you want to like impress your friends. You can tell them you're studying propositional calculus. What is calculus anyway? Where does that term come from? Anybody know?
I vaguely remember it's like, I think, it was that Newton that, well, I think about just calculus in general. Isn't it just like a funny word for math?
Sort of.
Like pebbles or something?
So it does come from calculating things, right? That's the calcul part of calculus. It's calculation.
Is it like,
So we just gotta figure out the Ulysses part.
Say again?
I said, so we just gotta figure out what the Ulysses part is.
Yeah. Anybody here know Latin? I don't even know if the people study Latin anymore. Latin's a great language to study, though. The Latin word for stone is like calcul or something like that. It means stone or pebble. and the Romans and Greeks, right? They used pebbles for doing calculations. So what's 2 plus 3? Well, here's 2 pebbles, and we put 3 more pebbles on. Oh yeah, there's 5 pebbles. Okay. So calculus is really, you know, a derived word for, you know, calculating, kind of like counting on your fingers, you know. But it's what we call calculus too. So propositional calculus is basically doing calculations involving propositions. Well, we're not adding and multiplying propositions, but we're still, you know, doing the kinds of things we do with numbers. We're putting things together, and we're getting new things out of old things. And any guess how old this subject is?
Well, it's either like 200 years old or it was like made last week.
So 200's not a bad guess. So mid 1800s, a person named George Boole did a lot of work to try to understand propositions, right? So this is Boole as in Boolean algebra. But the first known incidents of people studying formally logic and proofs and things like this is around 300 BC. And that goes back to Aristotle. So it's a very old subject. And in some ways, you know, George Boole took this calculus that was already developed and established and, you know, built it into something that worked with the idea of mechanical calculation, right? So something you could put on a difference engine or, you know, an Intel PC. So yeah, Aristotle, definitely. So when we talked about set theory, we said, you know, one of the things we want to do is create new sets out of old sets. So we learn how to take unions and intersections, and we can take a power set, and we can take a Cartesian product and things like that. Well, it's the same thing with propositional logic. One of the main things we do is create new propositions from old propositions. So we have a series of operations we can do on propositions. So the first one is called negation. So let me fix something up here. Let P, Q, and R be propositions. Actually, let me go ahead and name these. So I asked you to be careful about this. I should be careful about it too. So let's name these. Let P be the proposition. Today is Wednesday. Let Q be the proposition. I am the Queen of England. And let R be the proposition. We have a final today. Alright, so 3 propositions. P is the proposition today is Wednesday, Q is the proposition that I'm the Queen of England, and R is the proposition that we have a final today. So the truth value of this proposition P is it is true. And I'm just going to use T to represent true. Proposition that I am the Queen of England, that's false. I was deposed. And the proposition that we have a final exam today, that is also false. Alright, so 3 propositions with truth values. So we can create new propositions. So the first one is called negation. And we negate a proposition by putting this funny little symbol. It's a horizontal bar with a little hook on it, followed by a proposition. And this means not whatever that proposition is. the negation, or maybe in some sense the opposite of that proposition. So if P is the proposition that today is Wednesday, the negation of P, well, literally it means not today is Wednesday. But in English, we would probably say today is not Wednesday. And if I state a proposition that today is not Wednesday, that proposition is false, because today is Wednesday. So for this particular proposition P, not P would be false. And it turns out that, not P always has the opposite value of P. If I make a proposition not Q which says I am not the Queen of England, that's true. So not Q is true, Q is false. We do not have a final exam today, that's also true. That's the negation of this proposition which was false. So we could make, a little picture here and say, if P is false, not P will be true. If P is true, not P will be false. So we can draw something like a truth table.
Is this where P and P comes from?
P and P. What context?
That's one of those problems that haven't been solved yet.
Oh, P and NP. We'll talk about that at the end of the course. That's not where this comes from. That doesn't come from this. That has to do.
Awesome. We'll be talking about that.
It's what?
That's awesome. We'll be talking about that.
Yeah. We'll conclude the course talking about this famous problem, which is P versus NP. This is another one of those $1 million problems that, if you can solve this question, not only do you change the world, but you can get a bunch of money for it too. There's a lot of questions in this course that are like that. But there's probably easier ways to make money. All right, so this is a truth table for negation. So another operation we can do is called conjunction. And the only way I remember conjunction is conjunction, junction, what's your function, right? Otherwise, I get it confused with disjunction. So conjunction is an and, right? So P and Q means, well, it means P and Q. So the conjunction of P and Q is a new proposition. What does this proposition say? Today is Wednesday, and I'm the Queen of England. And that new proposition has a truth value which is false. Because, yeah, today is Wednesday, but I'm not the Queen of England, so I can't say that both of those are true. But if I had another proposition that was true, well, for example, I could do P and not R. And this means P and not R. Spoken and written English doesn't really have parentheses the way that we'd like, but you know what I mean here, right? I'm saying today is Wednesday and we do not have a final today. Well, that turns out to be true. Today's Wednesday and we don't have a final. Bye.
Bye.
See you later. And so we can write a table that shows us for any truth values of a pair of propositions P and Q, what does their conjunction look like? Well, if they're both false, then, saying P and Q is certainly going to be false. And if I say, I'm the Queen of England and today is Wednesday, that's going to be false. And if my first statement's true and my second one is false, that's going to be false. But if both statements happen to be true, today is Wednesday and it's light outside, right? That and is going to be true. So there's a truth table for conjunction. And yeah,
The symbol's the carrot, yeah?
yeah, that's a caret. And then to round this out, we have disjunction. And that's a V, or an upside down caret. And the disjunction of P with Q means P or Q. And you can guess how this works in all possible cases. If P and Q are both false propositions, then saying P or Q will also be false. But if Q happens to be true, then saying P or Q, yeah, that's true. Right? I'm the Queen of England, or today is Wednesday. Well, that's a true statement. Right? I'm going to do my homework today, or I'm going to do my homework tomorrow. Well, if I'm planning to do it today, then that or statement is true. If I'm planning to do it tomorrow, that or statement is true. I'm going to study today, or I'm going to study tomorrow. Well, if in fact I'm going to study on both days, this is still true. But this is one of these points where English kind of like means something different, right? Am I going to do my homework, or am I going to take a nap? Well, if I was going to do both, right, that or statement is still technically true, but when you ask someone that, you're kind of asking which of those are you going to do. You're kind of implying that there's a choice, right? So soup or salad kind of thing. But logically, this symbol just means the same thing it means in Boolean algebra. If this is true, or if that one is true, then this disjunction is also true.
Probably good to make the point too that, you know, they'll come up to you to ask soup or salad, but most places will be okay with both.
Well, yeah, probably. So let's see. So someone's handing you change in a store, and it's like, do you want ones or fives? Right? So the implication is I'm not going to give you your change in ones and then give you your change again in fives, right? But from a logic perspective, right, the answer would be, you know, true. I do want ones or I do want fives, whichever one I want, right? But in English, it kind of means, you know, tell me which one of these you want. So words like or, and, not, are less precise in spoken and written form than they are in propositional logic.
It's weird because the preposition soup or salad could still be a preposition if there's something akin to like an exclusive or, where you
Yes.
get one or the other.
And there is an exclusive or. I don't think we have a special symbol for it. I think it's still just the same old symbol we use in Boolean algebra. And that means one or the other, but not both. So
Is there a word for it?
I think it's just called an exclusive or. It doesn't come up very often for some reason, but we can formalize it other ways. But this looks, you know, just like a plain old disjunction, except if both of these are true, then it's false. All right, good. And you know, you may be noticing that this looks, you know, very much like that, like an intersection symbol, and this looks an awful lot like a union symbol. And we don't use these symbols for propositions, we use them for set theory. But we actually do use these symbols in Boolean algebra, right? In some instances, when you want to write a Boolean equation, as in Engineering 250, we'll actually use this V to represent an or instead of a plus sign. And we'll use a caret to represent an and instead of a dot. But they're definitely strongly in the domain of propositional logic. And then this is, you know, sometimes we use a tilde, like in programming languages, to represent negation. And that's partially a nod to this. There are some languages in which this is actually a symbol. I think PL1, this was actually part of the character set. and old key punches had this symbol on it, and you could actually like make that symbol, but it basically means not.
Is that what the tilde character turned into?
I wonder. I'm not sure. I don't know what a tilde does in plain old written text outside of the realm of computers. I'm not sure what the backstory on that is, but I'm sure there's tons of wiki pages on it. It's just funny, I've never looked it up.
I've read that there were a lot of arguments over trying to get rid of the pipe character, but
Oh, really? Because it looked too much
Yeah.
like a 1 and an I?
well, no, some company tried to start making keyboards that didn't have the pipe character, and
Oh,
everybody got real mad about it.
interesting. Well, yeah, and like keyboards are always fun because like if you go in the UK, the number sign is not where we're used to it, right? Number signs are sometimes called pounds, but if you look at a keyboard from the UK, Shift 3 is actually it's the symbol for a pound, right? And that's kind of fun. So yeah, keyboards are always interesting. Maybe that's a Shift
Yeah,
4.
I never thought about that before.
Yeah.
Like different symbol, because obviously they don't have dollar signs there; they have the pound symbol.
Yeah.
That's interesting.
So maybe it's the Shift 4 that's a pound sign. But yeah, and so on my keyboard right now, the pipe is drawn the way that I first learned to draw pipes, which was with a little gap in the middle. Right, and that's a little hard to see, but right there, that's my pipe symbol, and it's got a little space in between. Maybe to keep it from, looking like a 1 or an L or an I in some fonts. So, alright, so we can do the things that we've done in Engineering 250 with Boolean algebra, in, the beginning of this course with set theory, and now with propositions. A lot of these things carry over. Oh, Bosnian keyboards have the Z and Y switched. I didn't know that. That's cool. So for example, if I have a proposition P and I take the negation of it, I get a new proposition. If I take the negation of that, what would you guess I end up with?
Just
P.
propositional.
I end up with P. And I would draw, an equal sign with 3 lines, and this is a symbol for equivalence. Now technically, if I write an equal sign, I'm saying this is exactly the same thing as that. Well, here I made 1 stroke without lifting my pen. Here I had to lift my pen 3 or 4 times. They can't be the same thing, right? But logically they're equivalent. They mean the same thing. Today is Wednesday. Not today is not Wednesday. It's a double negative, which means this is logically saying the same thing as today is Wednesday. So we can look at equivalence of propositions, and we'll spend a lot of time doing that. But before we do that, let's go ahead and take our break, and then we'll come back and we'll talk about another way of forming propositions from other propositions, and then we'll start looking at properties of propositions. So let's do like a 4.5-minute break, and then we'll come back and continue
Did
with
we ever
this.
do an attendance thing this morning?
Yeah, I'll do an attendance when we come back. I think I forgot to do one in the beginning, but that's okay.
Okay, I just want to make sure I didn't miss it.
No, you're good. Alright, I'll be back in a few. All right, we're back. So go ahead and send me an attendance note. And I'll mention this again in a minute in case anybody comes back late. But you don't have to send me a second one. Just go ahead and send me one now. So let's talk about conditionals. So a conditional statement and I'm going to continue with the same propositions we had before. P is this proposition, Q is this, R is that, right? So a conditional statement is written like this. It's a proposition and another proposition with an arrow in between them. And what this translates to is if P, then Q. All right, so it's a conditional. And it's saying very precisely, if P is true, then Q is true. So let me change these propositions a little. Let P be the proposition. Today is Wednesday. Let Q be the proposition. We have CSE215 today. All right. So, if I ask you Q today, Q is true. If I ask you Q tomorrow, Q is false. Because tomorrow, if I say, do we have CSE? We have CSE 215 today, you would say that's a false proposition. If I asked you on the weekend if P is true or false, you would say P is false. All right, so P could be true, could be false. Q could be true, could be false. But here's something which is true. If today is Wednesday, then we have CSE 215 today. Forget about the fact that the class ends in December. Assume this is the rest of your life. You got 215 on Wednesday. If today is Wednesday, then we have CSE 215 today. And that is a true proposition. So this is called a conditional. All right, and you can write this by literally just writing out P, writing out Q, putting the word if in the beginning, putting the word then in between these. But again, English language, that's not always going to make sense because sometimes we reorder words in English. But this means if P, then Q. Or if you like, if P is a true proposition, then Q is a true proposition.
Does that apply for false as well?
No, it actually doesn't, and we'll see why in a few minutes.
So those both have to be true in order to be valid, right?
Not necessarily. So this is going to be a little odd. If P, then Q. If today is Wednesday, then we have CSE 215 today. So for example, let me come to it in a few minutes. Let me do some other setup first, and then we'll dig into when this is true or false based on P and Q. So this is called the hypothesis, and this is called the conclusion. And we'll use these terms a lot when we're talking about conditionals and about proofs. So the hypothesis is the thing that we're asking if it's true, and the conclusion is the thing that we're saying if the hypothesis is true, then the conclusion is true. All right. And in English, we can write this all kinds of different ways. So we could say if P, then Q. Sometimes you might see if P, comma, Q. If today's Wednesday, comma, we have class today. Sometimes we don't actually use the word then when we're speaking. Here's a bit of an odd one. Q is sufficient for P. So what does that mean? Sorry, I did that backwards. P is sufficient for Q. Having today be Wednesday is a sufficient condition for our having class today. Right? That's the only thing that has to be true to guarantee that Q is true. A necessary condition for Q is P. A necessary condition for today to be Wednesday is, a necessary condition for us to have class today is that today is Wednesday. And that can feel a little weird, right? We're not saying we only have class on Wednesday, but we are saying that if today is not, yeah, we are saying that. We are saying, let's see. I am like messing up.
Requirement to have classes that it be Wednesday?
Yeah, I'm messing this up in the worst possible way that I could, because swapping the P's and Q's is always bad. So let me try this again. A necessary condition a necessary condition for P is Q. In other words, in order for today to be Wednesday, we must have class today. And logically, that's a true statement. Logically, that's equivalent to if P, then Q. A necessary condition for today to be Wednesday is we have class. And logically, it does make sense, right? If today is going to be Wednesday, it's absolutely essential that we have class today. Why? Because if today is Wednesday, we have class today. Right? Given that that is a true statement, well, if we want today to be Wednesday, it's got to be a day that we're having class. But avoid the temptation to think of this as causality. It's not like if we decide to have class today, poof, it becomes Wednesday. And if I decide to cancel class, poof, it's no longer Wednesday. That's not what this is saying, right? If this really is a true conclusion, a true proposition, if today is Wednesday, then we have class, then this statement is also absolutely true. A necessary condition for it to be Wednesday is that we have class today.
Are there situations where these conditionals are reversible, and would that be considered something?
Yeah, we'll talk about those in a second, or in a minute, when we can swap around P and Q with each other.
I got a quick question. So, just for your example, how we have class Monday and Friday, can there be other conditions that also make Q true? Or
Absolutely.
If P is false, Q is not going to be true.
So I could say, for example, if today is Friday, then we have class today. And that's in fact a true statement.
So you could have another variable A saying today is Friday, and A, or if A, then Q.
Yeah,
also.
absolutely.
Okay, at the same time where if P is also Q.
Yeah.
Okay.
Wow, Zoom has like totally gone south on me.
What happened?
Well, so it was doing something earlier. I was trying to set people to have muted microphones when they came in, and it was giving me a good dialog box that was like totally empty. It just showed my background. And now I'm trying to click on the option to save my chat, and it's bringing up a pop-up that says more, and that's it. So it looks like everybody gets automatic attendance credit for today, but please don't leave just because I said that. Um, but you're all good for attendance, even if you're not here. All right, so we're working with if P then Q. And my point is just that there's other things that correspond to this that may not make sense. For example, Q if P. Right. Well, that's not so weird. P only if Q. Well, that's a weird one. But think about it. Today is Wednesday only if we have class today. That's a true statement. All right, so let's.
Do you have a P and Q reversed on the last one? Because that sentence means when it's today's Wednesday only if we have class.
This is true.
But in this, is it just like we're ignoring Monday and Friday, or? Because I thought we talked about how Q can be true with other conditions as well.
Mm-hmm. But this doesn't actually go against what you just said. Today is Wednesday only if we have class. Right? Today could be Monday. That's fine. It could be Friday. But today is Wednesday only if we've got class today.
This would be a false preposition then, right?
No, this is actually a true proposition. It's really weirdly worded, which is why I'm putting it here, right? Today is Wednesday only if we have class. So how else can we word that? Right, I mean, what this is saying is that if we don't have class, then today cannot be Wednesday.
Okay.
Right? So I'm putting this up here to warn you about this, but we're going to avoid this for the most part. Right? We're going to work in this very rigorous, very clean system of propositional calculus using symbology. But before we can get to that, we're going to need to start off with what we're given and what we're trying to prove and translate it into these nice symbols of propositional variables and conjunction and disjunction and so on. And that's where a lot of the mistakes can happen. Because, if someone asked you to prove this, well, that would be a kind of mean thing to ask. But if someone asked you to prove a statement like this, you would have to figure out what am I going to call P, what am I going to call Q, and what is this statement saying, right? So that's just something to be aware of. But we'll try to be more clear than this. The only way today can be Wednesday is if we have class. Yes, that's exactly the same thing. Yes, good way to put it.
Could you word it where you move the if in front of the today is Wednesday, so we have class? Would that still be the same preposition?
If today is Wednesday, then we have class. Yeah, it is.
Okay.
I believe so. If today is Wednesday.
That's why it would be a true proposition then, right?
Mm-hmm.
Okay.
All right, so let's look at truth tables. And this will get even weirder. So let me do the following. Let P be the proposition. X is bigger than 10. Let Q be the proposition. X is bigger than 5. Okay, let's think about the conditional. If P, then Q. What does that say? It says if X is bigger than 10, then X is bigger than 5. And let's just suppose we're working over integers. So this says if X is bigger than 10, then X is bigger than 5. So just from what you know about numbers and greater than signs, is this statement true or false?
True.
Everybody agree this is a true statement? If an integer is bigger than 10, then it's bigger than 5. Now, if I say, you know, hey, my number x is negative 17, is this proposition suddenly false? Or is this statement always true? If x is bigger than 10, then x is bigger than 5. And I think we can agree this is always true. Doesn't matter if I pick some weird value of x that's, you know, really big or really negative or what, right? This is still a true statement. So here's P, here's Q. And if P then Q should always be true, right? So let's pick some particular values of x and see what's going on. So for example, let's set x equal to 1,000. So is proposition P true or false?
True.
X is definitely bigger than 10, so P is true. What about Q? Is x bigger than 5?
Yeah.
Right? And we know that, you know, if P then Q is always true. Okay, let me pick a different value of x. Let me set x equal to 0. Is P true or false? Right? 0 is not bigger than 10. And what about Q?
It's also false.
That's also false. But remember, this proposition, if P then Q, this is always true. All right, let me pick another number. Let me set x equal to 7. So is P true or false?
It's false.
What about Q?
It's true.
That's true. And here the proposition is still true.
So is it no matter what, it's always going to be true, no matter what value of x you put in there?
Almost, with one exception. And the exception is our last row of this truth table, which is where P is true and Q is false. And if I could find a value of x that was bigger than 10, but less than 5, right, then this statement would be false. I would have a number that was bigger than 10, but not bigger than 5. So if I found some value where P was true and Q was false, then this proposition would be false. But it turns out I can't find a value of x where P is true and Q is false. That's kind of what this statement is telling me. But if I did, right, we can certainly agree, if this statement says if P then Q, and P is true, but Q turns out to be false, well, that if-then statement is also false.
So, let me get this straight on the first thing on the conditional table you have there. X equals 0, which would make P false and Q false. So if P is false, then Q is false, which is why it's true, right?
Yeah.
Okay. That's a little misleading at first.
Yes, it is.
But I think I get it.
So it turns out if P is false, this conditional statement is always true. It doesn't even matter if Q is true or not. And certainly if P and Q are both true, the proposition is true. That makes sense. And if P is true and Q is false, then the proposition is false. So these two rows usually make good sense in our common experience. But these two are pretty weird, and especially this first one. But from a logical perspective, writing if P then Q, if P and Q are both false, that condition is true. For example, if today is Wednesday, then we have class. Well, if today is not Tuesday and we don't have class, that statement is still true. If today is Wednesday, we have class. So that's fairly counterintuitive.
How exactly could P be false and Q be true, and then the conditional P to Q is true?
Well, for example, if x equals 7, P is false, Q is true. Right? X is not bigger than 10, but X is bigger than 5.
Okay, so if Q is true, then it's still true?
Mm-hmm. Anytime that Q is true, this will be true. Anytime that P is false, this will be true. And that's also kind of counterintuitive.
Can you say that one more time?
Anytime that Q is true, which are these two rows right here, the conditional will be true. And anytime that P is false, which is the first two rows, the conditional will be true. The only time the conditional is false is if the hypothesis is true and the conclusion is false. If this happens, then the conditional is also false.
So do we talk about the operation as sort of like, so long as it doesn't run into a false statement, it is true? Or do we talk about the operation more about the different states can be it?
It feels a little more like the first thing you said, if I understand you.
I mean, just as a whole, the idea that if x is greater than 10, then x is greater than 5. This is always true.
Mm-hmm.
Because we don't run into a state where it's false. But if I were to, I'm trying to give a good example, but just hypothetically, there is a number that is both greater than 10. It's greater than 10, but not greater than 5.
Mm-hmm.
Then that would then make the entire statement false. Would that be a thing that then it's always now false? Sorry. How will we speak of the statement then? If we
So this conditional would be if x was equal to, our magic symbol, which has this property that it's, bigger than 10 but less than 5. So if x was equal to our magic symbol, then for that value of x, this proposition would be false. Right? Which is what our truth table is also telling us. If we have our magic symbol that's bigger than 10, but it's not bigger than 5, then the conditional is false in that case. Now, for this proposition, there's no such x, and so that tells us that for all x we can think of, this proposition will be true. But that's just... Go ahead.
I think it's more of a thing about I don't know how to use it from here. It's the idea that we can create true statements and we can create false statements, but I don't know how to go. I don't know where to go from here and how then this can be really useful.
Yeah, we'll definitely work with this a lot, and we'll build on it. So someone said in chat, if P is false, then Q is true. Why is this not a false proposition? If P is false and Q is true, right? So that's like the case x equals 7. If I happen to pick a P that's false, that doesn't violate the fact that, if P happened to be true, Q would also be true. And that's what this conditional is saying. If P is true, Q is false. Well, if you give me a P that's not true, right, this makes no claim about Q. Q could be true or false, doesn't matter.
I think it might be better to see it sort of as Q is sort of like a property, quote unquote, of P. An idea that like Wednesday, a property of it being Wednesday is class.
Mm-hmm.
If it's Tuesday, we don't really care because we're not really talking about we're talking about Wednesday, not Tuesday.
Mm-hmm.
So there being class or not doesn't matter because it's not Wednesday.
Right,
So
right.
Have class, or not have class in the statement can still be true because
Yeah.
we're talking about Wednesday, not Tuesday.
Mm-hmm. So we don't need to make perfect sense out of this, and it's kind of fun actually to come back to this sometimes and wonder about it. But if we take this as being the truth table for a conditional, we can sort of work past the intuitive confusion. Um, but one final note on this, I mean, we actually use this in common speech sometimes. For example, someone might make the statement, um, if the Seahawks win the Super Bowl, I'm the president of the United States, right? And it's a way of stating an opinion that there's no way that the Seahawks are going to win the Super Bowl. It is so absurd that if it were to happen, I would, be the president of the United States. That's just as absurd, right? Well, what we're really doing there is we're exercising this first row of a conditional truth table, right? And we're stating something as being true and being confident in the statement of that as being true because we know the hypothesis is always going to be false. We know the Seahawks are not going to win the Super Bowl, right? And so we're stating that fact by the form of having a conditional where the conclusion is false but the conditional is true. So that's just a weird way to think about it. Apologies to any Seahawks fans. All right, so that's truth table weirdness. So let me do a couple of more definitions, and then we'll call it good. And we'll be working with conditionals a lot on Monday, and we'll play around with our truth tables more. And really, every time that we prove something, we're going to be using conditionals, right? So you want to prove that if it rains for the next week, then my plants are going to grow, right? That's a conditional statement. And how would you prove that? Well, you start off by assuming it rains every day and, deriving steps from that, and eventually write the proposition, your plants are going to grow, right? So conditionals will be at the root of most everything that we do. So let me come back to another topic that someone asked, and I said we get to. So converse inverse proposition. So suppose we have P and Q. Okay, this is the hypothesis. This is the conclusion. So if P, then Q. And again, P is the proposition. Today is Wednesday. And Q is the proposition. We have class today. Okay, so if P, then Q says if today is Wednesday, we have class today. And we've said that's a true statement. All right, we can also write if Q, then P. And this is called the converse. So the converse of if P, then Q is if Q, then P. Just switch around the hypothesis and the conclusion. And this says if we have class today, then today is Wednesday. So is that proposition true or false? If we have class today, then today is Wednesday.
False. False.
That is definitely false because, today could be Monday. We have class today, but today is Monday, so it's not Wednesday. So right there you can see a case where the converse is not logically equivalent to the original proposition. And proving something is false is easy in the sense that you only need one counterexample, right? This one example with these propositions, that's enough. We're done. We can say this is not logically the same as that. Proving two things are the same is a lot harder because you have to show they're the same for every possible thing you can think of, which is usually an infinite number of things. All right, there's another proposition we can derive, which is if not P, then not Q. And this is called the inverse. So the inverse of our original proposition would say, if today is not Wednesday, then we do not have class. So is that true or false? If today is not Wednesday, we do not have class. That's false, because on Friday, today will not be Wednesday, but we will still have class. So this is also not equivalent to that original expression. There's a third derivation we can make, which says not Q implies not P. If not Q, then not P. And this is called the contrapositive. And what about the truth value of that? If we do not have class today, then today is not Wednesday.
That would be true. Yeah.
That takes a lot more thinking, but that turns out to be true. If we do not have class today, today is not Wednesday, right? If you're not in class today, it can't be Wednesday, because every Wednesday you've got class. This is similar in spirit to what we do with De Morgan's theorem. It's not strictly De Morgan's theorem, although we'll see a version of De Morgan's theorem for propositions. But this has a different name. It's got a fancy Latin name, but most of us just call it the contrapositive. And it turns out that not only in this case was our original proposition true and our contrapositive was true, it turns out that these are logically the same. So we can write this is logically equivalent to if P, then Q. And we can prove that using truth tables when we get a little bit more machinery. And these cause all kinds of problems in the world. Because a lot of people don't understand that this is not the same as that. A lot of people believe that this is the same as that. And they're not. Logically, they are different, and they can have different truth values. They could have the same truth value, but they don't have to. And a lot of arguments that people get into and a lot of bad decisions that are made are based on the mistaken belief that, for example, this is the same as that. And logically, they don't have to have the same truth value. So I'll give you an example. If I donate $1,000 to Clark College, I really care about students. That's a true statement, right? If I'm going to donate $1,000 to Clark Foundation, then we can conclude I really care about student well-being. This statement says if I really care about student well-being, then I will donate $1,000 to Clark College. Well, that's not a true statement, because I do care about student well-being, but I don't have $1,000 to donate to Clark College. So this statement is false, even though that statement is true. But somebody would look at me and say, you know, how come you didn't give $1,000 to the college? You must hate students, right? That's a logical fallacy. But it's a mistaken belief that this is the same as that. And it's not. And you can, I mean, just hop onto social media, and it's mostly filled with incidents of, you know, failure to recognize this, or being upset that somebody didn't recognize this, and it just spirals out of control from there. So this is important stuff, right? There's a reason that we've been studying this topic for thousands of years, quite literally, right? Well, not we, you, and me, but humans have been studying this for thousands of years, um, and this is the basis for a lot of decisions. This is theoretically the basis for legal argument, and decision making processes in business and so on and so forth. So this is all topical stuff, and we are out of time. So Friday we'll talk about homework 1 a little bit. We'll take a look at homework 2, and then we'll continue developing the idea of propositions and building new propositions from old ones, and particularly looking at conditionals, and then from there, we will go into propositional equivalence, and this will get us into trying to show that two propositions are the same as each other. And that'll basically be our next stepping stone to getting to formal proofs. All right, my Zoom is broken. Everybody's got credit for attendance today. No need to do an additional attendance ping. So have a good one. I will see you next time. Thank you.
Adios. Take care.
See you later.
Have a good one.
Hey, Nick.
Yeah.
I got a quick question for you. Tomorrow I'm doing a trip back